Hello friends, today's topic of discussion is troubles in troubleshooting for cast and foundries. And to educate us, we have Mr. Subramanian with us. We have a specialist in gray, SJN and aluminum die casting. Currently, he is working as an independent consultant for last 10 years. The list of activities he is involved is long and include manufacturing process design, project planning and execution, and metallurgical process installation and monitoring, to name a few. He has presented many papers on IF and LUCAS platforms and authored books and DVDs for IIF, which are also available at NCTS, Pune, and these are also available on Amazon. There are two DVDs, A Journey Through Cold Works Process and Inoculation of Cast and Science and Practices, and a book on green sand practices for defect-free castings. Now, with this, I request Mr. Subramanian to take us through his presentation. Thank you.
Who doesn't have trouble? Keep writing troubles and troubles everywhere. If you can't see them coming, it is bliss. But when they come, it is annoying. Diagnosis is the bridge that connects symptoms of troubles with actions to follow. Which are they? The spotting the symptoms before a disaster. That's the most important aspect. And then diagnosing through the visible and invisible information. And getting the origins on board for appropriate preemptive action. Keeping a vigil for errors and judgments and possible course corrections. They're all part of the diagnostic exercise. And in a non-conforming casting, troubles are serious issues. What are the troubles? Basically, they are casting defects. A defective casting cannot be sold. When the boss is always in dilemma, when a casting defect appears, he is at crossroads. A finger on the process. He doesn't know. And then he gropes in dark. But there are aids, there are tools. He should be alert for all of them. So in this question, he has to find the right root cause and then proceed ahead for solving the problems. The classical name given to it is root cause analysis. The basics of it is very simple. So you have a weed that is obvious in a plant, which is obvious. I mean, you can see the weed. This is above the surface. What's below the surface is a bunch of roots, which are the underlying causes for the weed. We have to root out these so that you get rid of this weed, which is a symptom. The word root in root cause analysis refers to the underlying causes. Underlying causes, not one single cause. There are many roots. So we cannot say we'll catch one cause and then go over and find a solution, but tomorrow we may find another cause coming out and giving the same symptoms, and then you're not out of trouble anyway. So the causes is the catchword here again. Now let's talk about the symptoms, the weed that we said. What are the symptoms? These are the things which are obvious, but most of the time they are ignored. In medical diagnosis, you have symptoms seen in the ECG. It's a rhythmic pattern if there is nothing wrong. But when it's arrhythmic, you get a lot of symptoms. Arrhythmia, bradycardia, that's what causes trouble. Failures are common. To put it the other way, failures are not uncommon. They simply exist and fail to exit if the reasons are not known. We often seem to get over failures, and yet there are times we fail to resolve or solve these failures. The perception about the failures, it is the inability to meet an objective. Not able to meet that objective can be troublesome. And to be trouble-free, we need to shoot that trouble precisely. Random shooting leads to persistent troubles. So what are these objectives which we are not able to meet and they cause failures? Some examples, let us look at them. In the foundry field, you get the familiar casting rate, scrap rate. So it should be reduced from 3% to 1% is one of the objectives. So immediately anything above 1% becomes a problem. Another objective could be improve the yield from 60% to 70%. It could be a cycle time improvement, cut it down by 25% is the order. The inspection spend is too much today, so it should be limited to so many XXX rupees. That's a stipulation. Cost control. In terms of cost control, I will change the source which is cheaper, or I may land up with substandard material because of non-availability. These are some examples that can dramatically bring about troubles while trying to fulfill objectives. Standard operating procedures are relevant only within a stated parametric perimeter. But when the perimeter is altered, processes and procedures need a revisit. Let's take one example here. There is one change. The bentonite source change. What is the change? It has brought about a substandard material with MB value below the specification, methylene blue value below the specified value. Inventory controlled for segregated use of new and existing source. This is an immediate action that was taken. Yes, we know that source is different and then the value is less. So segregation activities started. Now let us look at the next scenario here. Having bought this, my processes are not going to be the same. So I need to do some tweaking. So the addition rate and the required compactability are altered. The bentonite quantity was increased because it is substandard. We have to meet that demand for strength in the mold. And because of this, the demand for water also went up. And then what are the consequences? Consequences, there is a drop in permeability. The mold is supposed to permeate all the internal gas pressures, which is difficult now. And because of the excess moisture, there are explosions inside the mold. And having bought this substandard material, there are fines more than what it used to be. And the obvious result is you get defects in the sand. So there's one change. You can see the number of changes that is happening down the line. And then the troubles are started. Addressing this trouble well in advance, yes, this is what is going to happen. So we need to take action before the trouble starts. Now let's see some scenarios. We hear it. Why is there an incident of cold lab defects? We didn't have before. Sir, the pouring hoist is making noise and plant maintenance has not attended to it. Pouring was not consistent. But behind this, the noise was not unusual. One trained pourer was absent and unskilled operative was the substitute. This is the reality. There are no castings available for dispatch. Why so many of them have been quarantined? Nodularity is less than 70% in the test coupon, sir. We cannot know. But actually, the test coupon was poured late, and the evidence was not captured or traceable. Upon subsequent verification, it was above 90%. So we have lost a lot of time before castings could be dispatched. We are losing valuable production time. Who is responsible for this? He is referring to overall losses. Broken molds are poured, they may leak. So he's also in tune with the overall losses concerned. So he's trying to pacify his boss. The fact is, match plates are not in good condition. That's what he says. But the mold breakage was actually due to jerks during the match plate stripping, and this fact was not reported. We have been making this item for the last 2 years without shrinkage defects. Rejections have increased. What is wrong with you guys? Total silence, nobody answered. And these are a few select conversations that illustrated why the reviews become ineffective and solutions remain far-fetched. Often the attitude is, it's not me, it's him. And let's look at the origin of troubles here. Simply put, some of these can be classified as the origins. Could be wrong decisions, disruptions, shift in focus, misconceptions, and the list is long, very long. You would see that wrong decisions, disruptions, shift in focus, misconception, all have a personal touch. Wrong decisions are made by people. Disruptions could be brought about by people, or it could be due to unforeseen circumstances. Shift in focus, basically the focus comes from the entrepreneur or the organization. Misconception is again people-oriented. Let's look at each of these contributors and look deep within what are the contributing elements in them. What are the wrong decisions possible? In the layout stage, when you put up a foundry, if you don't keep the furnaces close to the molds, as close as possible without disrupting any other process needs, you're going to have problem because of the distances. Temperature is going to be very low when the actual pouring starts. And there will be a lot of other issues. Inoculation might fade away. So it's important to think about a layout plan. The decision, wrong decision can come this day. The second could be tooling. Choice of the pattern material and the simulation that you do before you start making the tool. Once the tool is made, it's very difficult to maintain the quality of the tool for any iterations or alterations which you find later on to be very important. Then there is a decision about yield. There may be a general decision, I want 80% yield, and then you put the cavities in the casting in such a manner that you can get all those 80%. But when the problems arise, then you will see that your risering was inadequate or the gating system was absolutely wrong. You may have to forego 1 or 2 cavities in the bargain, and then yield is going to drop anyway. Core setting, you need to understand how you're going to lift the core and place the core inside the mold. So if it is a heavy core, if it is an assembly of multiple cores, then we have to think about core setting in a making wrong decisions there, because they are going to remain forever. Reconditioning, the type of cooler, the mixer that you use, the fines control, all are decisions. The core process, the binder that you choose, the coating that you have to do, and the storage and the drying, and all these are decisions that you have to make in advance. Casting finishing, how you are going to remove the gates, whether you are going to hammer them and do it, or you are going to have the cutter, which is hydraulic cutter, or how you are going to handle those castings. The use of filters, the type of filter that you are going to use, the application, all these are decisions that can go wrong if you don't pay attention. Let's talk about disruptions. It could be breakdowns, machine breakdown or power breakdown, which is not in your hands. Less manpower may be created due to pandemic, or maybe not available, or maybe boss pressures. Because of moisture during monsoon, there may be hygroscopic material in the coatings. There is a wear, there is a slag generation in the refractories used in the ladles and the furnaces. Molding sand can get hot in summer, or even if very heavy castings are poured day in and day out in 24 hours, and then the sand keeps on gathering heat. What is shift in focus? It's basically a management decision. Materials due to cost or the source change or source not a non-availability, downsizing the manpower, productivity shortcuts. This productivity shortcut is something which is very common. It's basically a deficiency in knowledge and knowledge to apply it. So there can be problems because of these. And so borrowing a parameter from your neighbor foundry is not a solution. You may understand certain things, but you need to adapt yourself for applying those. Let's look at some basics. It's not my intention to go through all the basics, but a few examples let us discuss here. But in the basics, this is a common understanding that everyone has. The mold filling being the ultimate in the process. The key support processes are, one is the mold making, the other one is the metal prep. Sub processes are core process and then the sand system which supply them to the mold. And then here is a solidification which we don't observe, but it is inside the mold after the metal is poured into the mold. So now together all these can form the key processes in the casting manufacturing process. So we'll look at some examples of these key processes and then just touch upon. One of the decisions we take in parting planes, selecting a parting plane, is either to have it at the top of the casting or at the bottom of the casting, in the middle of the casting. So each one has its own merits and demerits. So here you can imagine a lot of impingement at the bottom of the mold. Here you can see a lot of erosion at the bottom of the mold. Whereas this is about the metal path that you can follow. This system sand has this cyclic work to do. It starts with the sand preparation here, and then it goes to the molding area. Then the mold is closed with pores. Then it is ready for pouring. The cooled casting is shaken out, and then the sand gets really hot. And then sand has to be cooled. So now we'll see that this part of the process, this part of the cycle is the hot zone, and then here is the ambient zone. So now this has to be understood. The sand is hot in one part and then getting made to cool in the other part, and then you have to make a good mold. You need to do all these preparations and then make a good mold. That's the preparation for making a good casting. But the whole thing is not about chemistry alone. Most of us think that taking a spectrometer result when the metal is made is all that is required when the metal is poured into the mold. There's a lot of time spent between the analysis of chemistry and then the actual filling of the mold. Some example, let us see. One is about graphitization. Inside the mold, when the metal is cooling, there is solidification taking place. During the solidification process, we precipitate graphite in a controlled way. Now, here are some examples of uncontrolled way in which graphite can precipitate. E-type and D-type graphites, they produce carbide and unwanted graphite structures. The B-type is equally bad because some of this is the undercooled. Here is the carbide eutectic. Anything below this is likely to produce carbides. Whereas the A-type is the best suited. The C-type is producing very coarse graphite. The coarse graphite is a process where the austenite is the other constituent in the metal, which grows slowly. And when the austenite grows faster than the graphite, there is a heavier undercooling. So these are the situations where finer graphite is produced with a pronounced austenite growth. We can take another example of the metal, the holding of the metal after inoculation. Inoculation is the process of seeding nuclei in the liquid metal just before pouring. When you do the seeding, you get a lot of active micronuclei inside the metal. And as you hold the metal longer at that high temperature, there is a saturation in the liquid, and they migrate from one active level to another nucleus. So now there you will see that in this picture there are two nuclei which have lost their active shells. The elements have gone to the coarser ones. This is how it looks like schematically. Now, what is this? If you look at holding time, you see the finer nuclei get coarser and coarser as the holding time increases. And you'll see about 50% of this change called fading happens within the first 5 minutes. 5 minutes after the nucleant is added. That means after the first inoculation. So this process, so the finest nuclei are in the initial stage, then there is a migration to this stage, and then it's very coarse towards the end. This process is called Ostwald ripening, but it's enough to understand that the fading of inoculant is not just some few minutes or few seconds, but what is happening inside the metal is without these active nuclei, you cannot produce good graphitic structure. Let's look at some examples in troubleshooting. These examples are situations inside foundry. There are about 5 or 6. We'll go through one by one. Most of them are into one aspect, and as we go along, we will be able to look at them. Let's take the case of near case, which was leaking. The data on sand parameter had nothing unusual to say. They were combined and sand inclusions at the leakage zone. Now, what was missed? Erosion of sand at one ingate. This was a symptom which they didn't notice. Now let's look at what was done, or what was, and then what was done afterwards. So this is basically the gearbox, cold metal tendency on the cope side wall. There is a vertical wall here that is in this zone where mold was not getting compacted. It was fairly soft compared to the rest of the portions. So this was a softer mold. And you needed one ingate here so that you can avoid the cold metal tendency. So this filling the mold completely. But what was missed was the sand erosion that is taking place at this ingate. So something had to be done. The ingate is the source of the problem. So the ingates were altered, giving a certain direction towards the cold metal zone, and the problem. There was no sand erosion afterwards, and there was no cold metal also inside the casting. So another example we'll take, it's about the shrinkage in SGI and casting. It's a dizymatic match plate. It had a single riser feeding two identical castings. One casting always had shrinkage defect. Now this match plate is filled in a vertical position and then made horizontal and placed on the pallet. So one casting always had a shrinkage defect. So why the other one didn't have? That's a question. Shrinkage defect in SGN, first thing is look at riser and riser. Riser is common for both, but the riser necks are different. So riser neck dimensions were checked. In both the cavities, they were found identical. The missed symptom was a subtle bulge in the defective casting. They didn't notice there was a small bulge in the casting, which was showing shrinkage. So look at this. This is the match plate in which two cavities are put, 1 and 2. And this is the common riser. This is a screw through which the metal is entering. And this is the direction in which the sand is shot. So when it is getting shot, you see the cavity 1 is like this. And then the cavity 2 is like this. You know, this sand is finding it difficult to go around the pattern and then fill upwards. Here there is a direct approach to filling the sand inside the cavity. This is a hollow portion of the pattern, and this is a hollow portion of the pattern. So the casting becomes a shadow, and here there is no shadow, there is very good filling. So when the metal is poured and the riser is feeding the casting, the mold wall here was stopped and then it started yielding. So there was a bulge in the casting here. And then whatever the riser was able to feed was inadequate to feed the increased volume here. The bulge means the sand has moved away, so the requirement of metal has increased. So the riser is not able to feed because the neck is already dimensioned for only that much amount of metal that is calculated for. So what is the solution? Obviously, you cannot put the cavity like this. It has to be here. So relocating the cavity in the another example, scabbing is not the fault of sand. This is a title I gave. So it was assumed that the sand is responsible for scabbing and casting. So they were flywheel castings. They were suffering from scabbing tendencies, and the sand inclusions were there on the machine face. These flywheel castings are almost 90-95% machine, maybe 100%. All the faces. Nothing wrong was noticed in the data on the sand test results. So there is anything wrong with the sand. But scabbing is related to sand. A fully machine casting had no traceability indicator. So that means once you machine it, you don't come to know which part of the casting is traceable to the actual positioning of the cavity inside the pattern. The meaning is, if there is an ingot, I should be able to know how this casting is getting filled. So the traceability is missing in a machine casting. This symptom was that the scab was always in front of the single gate provided to each cavity. So the scab was formed in front of the ingot. That was missed because once the casting is shaken out and dressed or fettled, it's difficult to find out unless you have some marks. And at that stage, nobody ever marks those castings. It goes for machining directly, and then that's how it is missed. So this is how the layout of 4 cavities in the pattern, and then there is a single gate to each cavity, and the scab was found in this position right in front of the gate. So the solution was to provide 2 gates, not exactly at right angles to the casting, but at an inclination to the casting, whereby you can effect a circular motion to the filling metal. The advantage is very simple. It doesn't allow the metal to over, like in this case. So it keeps circulating. So there is an average temperature of the metal as it moves around. And then there's no single location where the sand is going to get overheated. So this is the overall layout where each cavity is having two inlets tangential to the perimeter. So the scabbing vanished. So nothing to do with the sand system here. Now we are using a ceramic filter, but the dross is not getting trapped. So it's a paradox. These SGN castings had severe incidence of dross inclusions. Metal cleaning was given the utmost priority. Filter placement was kept under constant surveillance. What I thought was metal is dirty, so dross is coming. The other thing is somebody might be missing, or somebody might not be keeping correctly. So there is a supervision, 100% supervision to see that this is okay. But symptom was an error in tooling that went unnoticed. Let's see what was wrong in that. So this is the layout. There are 4 cavities in this layout. There are 2 risers. And this is a common runner here and common runner here. And these are the gates. You know, a section across this is shown here, where the filter is here, and then the down screw is here, and then the 2 branch run. You can see that metal is directly going past here. It is supposed to go through the filter, and then you are having some metal going through the gaps here, and that gap is allowing dross material to enter the runner, and then it goes to the cast. Unfiltered metal entering the primary runners. This was not noticed. Anybody who is very vigilant could have gone to the shakeout and seen the cool down bunch. He would have found out this error is obvious. Later on, this flare out is reduced so that the gap is eliminated. The moment that is done, only filtered metal was allowed to go through, and then you got a clean metal without any dross. Another example is breakage of ceramic filter. Gray castings showed broken filter particles when machined. This was the observation. The immediate reaction would be, oh, so filter is breaking, so the filter is a problem. Filter supplier was taken to task. There was a conceptual error in the application of filter, and that was the reason for breakage of filter. It's difficult to imagine that way, but let's see what is the actual. You'll see the before filter breakage. That is, the filter breakage is an issue. So during that, before and after the taking action, before it was taken, there was filter breakage, and this filter is put here, and this is the casting, and then the metal is entering the casting. When the layout, it looks like this, and then there are gates here, and then this is a filter. Quite common to put the filter in this position just next to the down screw valve, and this is how it looks. The filter is very small, and the filter here, the filter becomes a choke. And the coverage by the filter for filtering is also, you have a runner bar which is of a certain area, let's say A, and you put a filter here, and the filter has got some solid obstructions. Obviously, the area A inside the filter is going to be less than A. So this becomes a choke. Now, what is this choke? So when there is a choke, there is a pressure buildup behind the filter. And then the velocity across the filter increases. And so these two adverse factors, with a higher temperature, which is from the hot metal, over a period of few seconds allows the filter. The pieces of the filter is carried through the running system into the cast. The ideal thing could have been to change the size of the filter, a larger one. Nowadays, filter manufacturers give you guidance as to what size of the filter you have to choose and what is the amount of metal that it can flow through. So this is the way in which it has to be put, and then the runner bar has to be expanded and contracted again. So the area A here and area A here are same, whereas around the filter, it is much, much higher than that. The thumb rule is for gray cast iron, you have to use an area of the filter which is 3 times the area of the runner. In SGI, you may have to go up to 4 times the area of the runner. But these are only thumb rules, but you have to decide based on the situations. So the larger pore coverage gives you uniform pressure across the filter, and there is no pressure buildup because the moment the metal is going past this area A into an area which is much larger, there is a pressure drop. This pressure drops allows dross particles to or slag particles to float in, and the velocity across the filter is reduced. So there is no pressure on the filter, there is no force applied on those filter particles. And enough opportunity to stay behind the filter. The metal that comes out at this very clear, and they enter the runner again at the area. Other dynamic kinematics are maintained as before. Whatever is here is maintained here, minus some losses across the filter. An example could be again dross in the SGI castings. Initially, the SGI castings had sand inclusion defects. Now, this is an example where an action was taken for sand inclusion. So they had sand inclusion defects in those castings initially. Then there was a pattern maker who was having good experience, very highly experienced person. He had a brilliant idea. So he said, let's change the cope to drag and drag to cope. And he was given the full responsibility to execute that, and he did it overnight, and the trials were taken. And he was good. Sand inclusions definitely vanished, but in came dross in a big way. Poor fellow, he was questioned again. What are the missed opportunity? The implementation of the brilliant idea was executed poorly. What is the problem? How it was missed? Let's see. Now this is the layout here. 6 cavities and one single riser connecting 3 cavities, one single riser connecting 3 cavities. And then you take a section across this. When he did that cope to drag interchange, he made an error. The metal that is coming from the down screw was not going through the filter. It was directly entering the riser. He forgot to change piece of the runner and put it at the drag. So this is how the modified running system looked. So the runners here were put here, and then obviously the filtered metal only can enter the runner and into the casting lick. So sometimes in our hurry we may miss out some of these finer issues, and then we pay for it heavily. Here is an example which is not gating system, but it's a cast iron cylinder head. Cast iron cylinder heads they have a lot of stud mounting holes which this cylinder head gets attached to the cylinder block casting by bolting through these holes. Now these holes are having solid wall around the holes, and then inside of this solid wall, there is water circulating. In a manufacturing process, the water circulation is provided by a water jacket core, a core which is made of core sand binders. That either it could be a shell core binder or a cold box binder, and that sand core provides a empty space behind the stud hole. And there are many stud holes in the cylinder head, and it was found that a couple of stud holes were leaking. Leaking in the sense when they machine the stud hole and then they do a pressure test for the water leakage. They found that the water was entering the stud hole, which is not supposed to happen. It was analyzed, and they found the presence of micro shrinkage in that metal around the stud hole. So they tried classical methods of combating this micro shrinkage, basically working on pouring temperatures, carbon equivalent percentage, the amount and type of inoculant. So everything was centered around the metal because everyone thought a metallurgical defect like micro shrinkage has to be attacked through the metal route only. Classic study. The missed opportunity is a worn-out tooling for water jacket core. I mean, who would have thought that a water jacket core could be responsible for a shrinkage? So let's see some pictures. And here is the cylinder head with the stud mounting holes here. And this is the water passage. This is the water passage. So this water passage is created by this blue colored water jacket core. And then this water jacket core is produced from a core box which produces this. You can see a line here. This is the parting line in the core box. Now, in this present case, this parting plane was not trimmed properly. And in some couple of holes, what we are talking about, the fins could not be removed completely. Normal process, one would just take a trimming tool like a memory paper and make it a cylinder and then poke it water jacket holes. But for some reason, he is not in his normal process of trimming the core. He is not doing a complete trimming of this fin in some problematic stud holes. Yes. What we are talking about here, and then this is the wall around the stud hole, and then this is the shrinkage zone. This is the blue thing is the water jacket core, and this is the parting line fin. Just behind the shrinkage. Shrinkage is the fin, and this machined opening here, and then the water was leaking through this point. See, if this fin is not trimmed at all, we can imagine that the fin is extending up to the hole and then directly leaking. It's not something we found out. But here, a partly trimmed core, which is leaving a certain edge here, and then it can create a shrinkage here. Now, this is actually at the tip of a core fin. Now, all of us know that a riser in SJN is given a notch at the top of the riser. That notch helping to keep the riser hot. Below the notch of the riser, the metal remains hot because a hot spot is developed below that. The modulus of the section is highest at that point. Now here again, you have a modulus created here because there are surfaces here which are getting heated with the metal. So you are creating a hotspot, and then the modulus here increases, and then the shrinkage demand is not met by the cooling forces here. So from these examples, we see a reality. Let us see, this is a chimney here. How tall is the chimney? So we stand somewhere nearby and then try to guess what will be the height of the chimney. Take another case. We go a little farther from it. Then look at the same chimney in the perspective of a nearby object, nearby building, or nearby tree, or whatever. And then we are able to guess relatively what is the height of this building and what could be the here. And then we have a better perception and we can answer the question quickly. So friends, in root cause analysis, peripheral observation is essential in problem solving, like we saw in the case of chimney. And the water jacket or fin. Root cause analysis is not just about one single cause. Corrective action for one cause may miss out on other relevant causes. So address all the significant factors responsible for the problem. Summing back, so we look at the root cause analysis basics. These are the obvious weeds, and these are many roots, which are the causes. So we have to look at all the causes to find out solution. So thank you for your patience.
Mr. Subramanian, it's a very, very, very interesting session. Your case studies have put life into your presentation, and that was we look forward. So very, very elaborately explained case studies, and I think all of us here benefited with that.